Hi, this is the lecture on water and aqueous systems. It is the lecture that precedes solutions. The underpinnings of solutions will be discussed here. In a water molecule, the bond polarities are equal, but the two poles do not cancel each other because a water molecule is bent. The molecule as a whole is polar. So it's the geometry that makes something polar. Carbon dioxide, which is a linear molecule as we studied with molecular geometry, those dipoles cancel. But if something has an irregular shape, it does not. Recall that water is a simple triatomic molecule, H2O. The oxygen atom forms a covalent bond with each of the hydrogen atoms. Because of its greater electronegativity, oxygen attracts the electron pair of the OH bond to a greater extent than hydrogen. As a result, the oxygen atom acquires a partial negative charge. That's lowercase delta plus and lowercase delta minus. The less electronegative hydrogen atoms acquire partial positive charges. Thus, the OH bonds are highly polar. How do the polarities of two OH bonds affect the polarity of the molecule? The shape of the molecule is a determining factor. The bond angle of the water molecule is approximately 105 degrees, which gives the molecule a bent shape. The two OH bond polarities do not cancel, so the water molecule as a whole is polar. The net polarity of the water molecule is illustrated here in figure 2. They don't cancel because of the geometry, so that's very important to study. The geometry of molecules based on the electron organization of the valence shell and how they relate to atoms, other atoms in bonds with them. So it's not polar because of that, because of the organization of the geometry of the molecule. The polarity of the water molecule results in hydrogen bonding. Partial negative charges are on each oxygen atom. So you have 2 times the partial charge negative, partial charge positive on each hydrogen. You have different views of it. They're forming hexagonal rings. In general, polar molecules are attracted to one another by dipole interactions. The negative end of one molecule attracts the positive end of the other. Figure 3 shows how this intermolecular attraction among water molecules results in the formation of hydrogen bonds. Many unique and important properties of water, including its high surface tension and low vapor pressure, yes, I said that correctly, low vapor pressure, results from hydrogen bonding. Let me ask you a question. Why is it important for our survival on Earth, human survival, for water to have a high vapor pressure? That's an extra credit question, and first person that tells me in class will get the extra credit. Okay, now, notice the two-dimensional organization of the molecules because of hydrogen bonding. That results in more space that things can dissolve in. Surface tension makes it possible for some insects, such as this water strider, to walk on water. Water molecules at the surface of the water drop above cannot form hydrogen bonds with air molecules, so they are drawn into the body of the liquid, producing surface tension. So you can see how surface tension is involved here. It's the organization of the water molecules relative to hydrogen bonding which causes the high surface tension. And soon we'll learn how to reduce that water tension, how to decrease the hydrogen bonding that causes the surface tension. A water droplet forms because of surface tension. Have you ever seen a glass so filled with water that the water surface is not flat but bulges above the rim? Or have you noticed that water forms nearly spherical droplets at the end of a medicine dropper, or when sprayed on a greasy surface? Let me just say one thing, that the formation of a bubble and the formation of a droplet is completely different. I'll talk about that more in a moment. The surface of water acts like a skin, as a water strider shown in figure 4 demonstrates. This skin-like property of water's surface is explained by water's ability to form hydrogen bonds. The molecule within the body of the liquid form hydrogen bonds with other molecules that surround them on all sides. It's actually the hydrogen bonds that prevent bubbles to be formed. A droplet has water on the inside. A bubble has air on the inside, or whatever the environment is. So why is that different relative to hydrogen bonding? That's another question, which I will give extra credit for the first person. Let's say the first 5 people to tell me that will also get extra credit. So the attractive forces on each of these molecules are what? Okay, look at that drawing. The inward force or pull that tends to minimize the surface area of a liquid is called surface tension. All liquids have surface tension, but water's surface tension is higher than most. The surface tension of water tends to hold a drop of liquid in a spherical shape. The drop is not a perfect sphere because the force of gravity tends to pull it down. I got to change the timing on that to finish that. Hold on. Let me read that last sentence again. The drop is not a perfect sphere because the force of gravity tends to pull it down, causing it to flatten. Especially when it's falling, it kind of wobbles around a little bit. But with all that aside, it will form a sphere. This is why on some surfaces water tends to bead up rather than spread out. It is possible to decrease the surface tension of water by adding a surfactant. A surfactant is any substance that interferes with hydrogen bonding because water molecules and thereby reduces surface tension. Soaps and detergents are surfactants. Adding a detergent to beads of water on a greasy surface reduces surface tension, causing the beads of water to collapse and spread out. Causing them to collapse and spread out. You can do it at home on a pan on the stove. It's kind of cool, actually. Do the two. Yes, you have surfactants. No, you don't have surfactants. Try that at home and see if you can do that. Take pictures of both, and I'll give you extra credit if you show that to me on your camera. Let's say the first 5 to do that as well. Hydrogen bonding between water molecules also explains water's unusually low vapor pressure. Remember that the vapor pressure of a liquid is the result of molecules escaping from the surface of a liquid and entering the vapor phase. Because hydrogen bonds hold water molecules to one another, the tendency of these molecules to escape is low, and evaporation is slow. Imagine what would happen if it were not. All the lakes and oceans with their large surface areas would tend to evaporate. What would that do to quote-unquote weather systems around the world if you have all of this gaseous material in the atmosphere? What would happen to the atmosphere? What would happen to storms? You have seen that water in the liquid state exhibits some unique properties. The same is true for water in the solid state. For example, ice cubes float in your glass of iced tea because solid water has a lower density than liquid water. This is not usual for liquids. As a typical liquid cools, it begins to contract and its density increases gradually. Increasing density means that the molecule of the liquid move closer together so that a given volume of the liquid contains more molecules and thus more mass. If the cooling continues, the liquid eventually solidifies with a density greater than the density of the liquid. Let me change the timing on this. We'll be right back. Because the density of a typical solid is greater than that of the corresponding liquid, the solid sinks in its own liquid. As water begins to cool, it behaves initially like a typical liquid. It contracts slightly and its density gradually increases, as shown in Table 1. So you see that it's getting more dense as you go down to 4 degrees, and then it gets less dense. Kind of weird. But so listen carefully. For a lake to freeze, therefore, why is this true? Map it out on a piece of paper for extra credit. The entire lake has to be 4 degrees before it can cool to 0 degrees. The entire lake must be 4 degrees. That's the tough one. Here's another picture. Extensive hydrogen bonding in ice holds the water molecules far apart, more ordered arrangements than a liquid water. The hexagonal symmetry of a snowflake reflects the structure of the ice crystal. This is a two-dimensional drawing. Think of a tetrahedral model where it forms a tetrahedron with all of the parts of the water molecule bonded or not bonded members, and it forms kind of a tetrahedron, a physical tetrahedron, which gives it that lustery diamond look. Why is ice less dense than liquid water? As you can see in Figure 5, hydrogen bonds hold the water molecule in place in the solid phase. The structure of ice is a regular open framework of water molecules arranged like a honeycomb. When ice melts, the framework collapses and the water molecules pack closer together, making liquid water more dense than ice. The fact that ice floats has important consequences to organisms. Can you imagine if ice formed at the bottom and proceeded upward, and the lake, the fish would have very little water to swim in? Remember that the fish breathe just like humans, except that the oxygen exchange location requires more water. It tends to be more wet than lungs, even though lungs are very wet as well. But they still have an oxygen exchange center like we do. A layer of ice on top of a pond acts as an insulator for water beneath, preventing it from freezing solid except under extreme conditions. Because the liquid water at the bottom of an otherwise frozen pond is warmer than 0 degrees Celsius, fish and other aquatic life are better able to survive. If the ice were denser than liquid water, bodies of water would tend to freeze solid during the winter months, destroying many types of organisms. Ice melts at 0 degrees Celsius, of course. So what would that have to do with our survival if water froze at the bottom, let alone fish? Although fish is very important as well. But if something goes extinct during your lifetime, all humans lose a little piece of their own life because of the extinction of animals. We're doing something wrong on the planet. We have a symbiotic relationship with everything on the planet. Everything has a reason, so it's very important to understand those physical factors. This is a high melting temperature for a molecule with such a low molar mass. A considerable amount of energy is required to return water molecules to the solid state in the solid state to the liquid state. The heat absorbed when 1 gram of water changes a solid to a liquid is 334 joules, or 80 calories, scientific calories. Remember that they're using joules because it's kinetic energy. Kinetic energy, potential energy, work, it's all a measure of, in joules, mechanical energy. You can convert it to calories. And also remember that to go from a liquid to a gas, it's going to be 540 calories as opposed to 80 calories. So that's going to be many times, 6-7 times as much energy. So that's also very important to understand that jump as well. This same amount of energy is needed to raise the temperature of 1 gram of liquid water from 0 degrees Celsius to 80 degrees Celsius. So it's a lot of water. It's called the heat of fusion. So 334 joules per gram is the heat of fusion of water, and so that's a lot. So it's not easy to freeze water. Water molecules are in continuous motion because of their kinetic energy, again, joules. when a crystal of sodium chloride is placed in water, the water molecules collide with it. Now we're getting into the beginnings of solvation, the beginnings of the solution process. Solvation is the solution process, how these hydrogens come in and line up with the chlorines and the oxygens with the sodium, and it rips the sodium chloride apart. Remember that water molecule is polar, with a partial negative on the oxygen atom and partial positive on the hydrogen atoms. The polar solvent molecules, H2O, attract the solute ions, Na plus, Cl negative. So now we're beginning to get into the solvents. Those things that give it high surface tension are the same things that will help it be a universal solvent. As individual solute ions break away from the crystal, the negatively and positively charged ions become surrounded by solvent molecules and the ionic crystal dissolves. The process by which the positive and negative ions of an ionic solid become surrounded by solvent molecules is called solvation. Figure 7 shows a model of solvation of an ionic solid such as sodium chloride. In some ionic compounds, the attractions among the ions in the crystals are stronger than the attraction exerted by water. Now I say figure 7, but really what I'm talking about, I have many figures on the solvation process, many images that I put in there to help you understand. And it's actually one of the simpler things in chemistry. You have a polar molecule. Why it's polar we learned many months ago, and now we're putting it to work in a dynamic process where the water is literally taking apart the sodium chloride and surrounding it. These compounds cannot be solvated to any significant extent and are therefore nearly insoluble. Barium sulfate and calcium carbonate are examples of nearly insoluble ionic compounds. Figure 8 shows that oil and water do not mix. But what about oil in gasoline? Both oil and gasoline are nonpolar. The attractive forces that hold two oil molecules together are similar in magnitude to the forces that hold two gasoline molecules together. Oil molecules can easily separate and replace gasoline molecules to form a solution. So it's a little bit different with oil and water. That one slide seemed a little out of place. We're talking about the solvation process, and then we're talking about insoluble ions. But the idea is, even if it's an ionic substance, it doesn't mean necessarily that it's going to be soluble. There are a lot of salts that don't dissolve in water, or dissolve very poorly. Calcium carbonate is one of them, as they said. Why is that so significant? Well, look at a lot of sea creatures, clams and lobsters and crabs. Their shells are made of calcium carbonate. If calcium carbonate could dissolve in water, then what would happen to those organisms on this planet? So calcium carbonate doesn't dissolve, which is a good thing. And there are other salts, and we'll learn rules. If you take another chemistry course, like IB chemistry or AP chemistry, you'll learn actual rules for the solubility of salts, where you can actually look at a salt now and look at its ions, and it won't dissolve. Another salt that will not dissolve, which is a good thing, is calcium phosphate, which is bone. Can you imagine if bone dissolved? You're mostly water. You'd be a bag of bloody tissue. You wouldn't have any skeletal structure. It would all melt, and you'd be a giant blob on the floor. Would not be pretty. I stopped the tape and looked back on the discussion that we had, and it did look like that slide was out of place, but I'm going to leave it there. Barium sulfate and calcium carbonate are insoluble. They do not go through the solvation process because of the combination of ions, sulfate and barium. There's something about that combination. Calcium and carbonate. There's something about that combination that doesn't seem to want to separate well. Also on this slide is a picture of Gatorade. Now, Gatorade was formulated for athletes, and I did a lot of reading on it. The next several slides are taken, I believe, from Wikipedia, which is a very good source. It's a beginning source, but you got to be careful with any source, not just Wikipedia. But I did a lot of checking, and it seems pretty legit stuff. I would suggest doing some reading on your own to see, but it certainly was inventive. I think it's great stuff. But if you're an athlete and you're constantly sweating, you have to replace something called electrolytes in your system. You hear that a lot in sports, because when you sweat to cool your body, because the sweat has a high specific heat capacity, the water will absorb the energy from the body and evaporate, thereby cooling the body. Well, unfortunately, what comes out of the body with the water are salts. And water by itself does not conduct electricity. Water does not conduct electricity. Salts do. Well, you have a lot of electricity in your body. So you need things dissolved in the water in your body to help maintain the integrity of the metabolism that the body goes through in order to live for life. So it's pretty legit, but I would encourage you to do reading on your own to make your own decision about Gatorade. I'm not advertising it. I just think it's a great example of the concept of electrolytes and how electrolytes are very important for your own metabolism. So we'll start right away on the next slide, which will be Gatorade. Gatorade was formulated in 1965 by a team of researchers at the University of Florida College of Medicine, including Robert Cade, Dana Shires, Harry James Free, and Alejandro de Quesada, following a request from the Florida Gators football head coach Ray Graves. Gatorade was created to aid athletes by acting as a hydrating replacement for body fluids lost during physical exertion in hot weather. The earliest versions of the beverage consisted of a mixture of water, sodium, sugar, potassium, phosphate, and lemon juice. So right away, you see that there are some electrolytes. We have phosphate, we have potassium, we have sodium. Sugar is not an electrolyte. The 10 players on the University of Florida's football team tested the first version of Gatorade during practices and games in 1965, and the tests were deemed successful. On the other hand, star quarterback Steve Spurrier demurred, "I don't have any answer for whether the Gatorade helped us be a better second half team or not. We drank it, but whether it helped us in the second half, who knows?" Nonetheless, the football team credited Gatorade as having contributed to their first Orange Bowl win over Georgia Tech Yellow Jackets in 1967, at which point the drink gained traction within the athletic community. Steve Spurrier is, I think, a well-known athlete. Yellow Jackets coach Bobby Dodd, when asked why his team lost, replied, "We didn't have Gatorade." That made the difference. The University of Florida researchers initially considered naming their product Gatorade. They settled on the name Gatorade, however, since the researchers wanted to create a commercial product, not a scientifically validated one. Darren Rovell notes in his History of Gatorade, "First in thirst, the doctors realized that they probably shouldn't use the "aid" suffix, since that would mean that if the drink were ever marketed, they would have to prove that it had a clear medicinal use and perform clinical tests on thousands of people, which did not happen. Gatorade co-inventor Dana Shires explained, "We were told that you couldn't use that because the FDA, Food and Drug Administration, prohibited that. That would classify it as something other than a cola or soft drink. So we changed it to ADE, aid. For example, some were skeptical that the product's effect was anything more than the placebo effect." Cade mentioned, "If you told a football player that you were giving him Demerol to relieve pain, and you gave him a placebo instead, there's about a 30% chance that that placebo will relieve the pain as much as taking Demerol would have." Shortly after the 1967 Orange Bowl, Robert Cade entered into an agreement providing Stokely Van Camp Incorporated, SVC, a canned food packaging company, with the United States rights to production of the sale of Gatorade as a commercial product. In the same year, a licensing agreement made Gatorade the official sports drink of the National Football League, the NFL, representing the first in a history of professional sports sponsorship for the Gatorade brand. A year after its commercial introduction, SVC tested multiple variations of the original Gatorade recipe, finally settling on more palatable variants in lemon, lime, and orange flavors. As of 2009, the university had received more than $150 million from its share and was receiving approximately $12 million per year. University of Florida football player Chip Hinton testing Gatorade in 1965, pictured next to the leader of its team of inventors, Robert Cade, and that was taken from Wikipedia, a wonderful source. As a rule, polar solvents such as water dissolve ionic compounds and polar compounds. Nonpolar solvents such as gasoline dissolve nonpolar compounds. The relationship can be summed up in the expression like dissolves like. And there's a picture of some solvation of a crystal and how the hydrogen bonding is affecting that. And here's another example of the hydration of the crystal, essentially hydration, where I'm taking the sodium chloride crystal apart by using the hydrogen bonding of the water and the dipoles that are created, the net dipoles, and I am surrounding each ion by the correct orientation of the water. A solvent, let's talk about solvents for a minute. A solvent, from the Latin salvo, I loosen, untie, I solve, is a substance that dissolves a solute, a chemically different liquid, solid, or gas, resulting in a solution. A solvent is usually a liquid, but can be a solid or a gas. The maximum quantity of solute that can dissolve in a specific volume of solvent varies with temperature. Common uses for organic solvents are in dry cleaning. Example, tetrachloroethylene, as paint thinners, toluene, and turpentine, as nail polish removers and glue solvents such as acetone, methyl acetate, ethyl acetate, in spot removers such as hexane, petroleum ether, in detergents, citrus terpenes, in perfumes, ethanol, nail polish, and in chemical synthesis. The use of inorganic solvents other than water is typically limited to research chemistry and some technological processes. The global solvent market is expected to earn revenues of about US dollars 33 billion in the year 2019. The dynamic economic development in emerging markets like China, India, Brazil, or Russia will especially continue to boost demand for solvents. Specialists expect the worldwide solvent consumption to increase at an average annual rate of 2.5% over the subsequent years. Accordingly, the growth rate seen during the past 8 years will be surpassed. You would never think it, but $33 billion by the year 2019. The dynamic economic development emerging markets like China, India, Brazil, and or Russia will especially continue. It's unbelievable. When one substance is dissolved into another, a solution is formed. This is opposed to the situation when the compounds are insoluble like sand in water. In solution, all of the ingredients are uniformly distributed at a molecular level and no residue remains. The mixture consists of a single phase with all solute molecules occurring as solvates, solvent-solute complexes, as opposed to separate continuous phases as in suspensions, emulsions, or other types of mixtures. The mixing is referred to as miscibility, whereas the ability to dissolve one compound into another is known as solubility. This is the section on solutions and solvation. Again, this was taken from Wikipedia. However, in addition to mixing, both substances in the solution interact with each other. When something is dissolved, molecules of the solvent arrange around molecules of the solute. That's solvation. Heat is involved and entropy is increased, making the solution more thermodynamically stable than the solute alone. This arrangement is mediated by the respective chemical properties of the solvent and solute, such as hydrogen bonding, dipole moment, and polarizability. Entropy is disorder. When something is packed like a nice crystal, that's very low entropy. It is natural to increase entropy, and entropy can be increased, or randomness can be increased, by putting something into solution. So if you're increasing entropy, that makes things thermodynamically more stable. One of the laws of thermodynamics has to do with entropy. Solvent classifications. Solvents can be broadly classified into two categories: polar and nonpolar. Generally, the dielectric constant of the solvent provides a rough measure of a solvent's polarity. The strong polarity of water is indicated at 0 degrees Celsius by dielectric constant of 88. Solvents with a dielectric constant of less than 15 are generally considered to be nonpolar. Technically, the dielectric constant measures the solvent's ability to reduce the field strength of the electric field surrounding a charged particle immersed in it. It is not important that you understand the theory of the dielectric constant. What's important is the higher the dielectric constant, such as 88, the more able the solvent is to dissolve a polar solute, and the lower that number is, such as less than 15, the more difficult it will be to dissolve a polar solute. Okay, this reduction is then compared to the field strength of the charged particle in a vacuum. In layperson's terms, dielectric constant of a solvent can be thought of as its ability to reduce the solute's effective internal charge. Other polarity scales, dielectric constants, are not the only measure of polarity. Because solvents are used by chemists to carry out chemical reactions or observe chemical and biological phenomena, more specific measures of polarity are required. We will not discuss those here. They are way beyond the scope of this course. Not to worry. The polarity, dipole moment, polarizability, and hydrogen bonding of a solvent determines what type of compounds it is able to dissolve, and with what other solvents or liquid compounds it is miscible. Generally, polar solvents dissolve polar compounds best, and nonpolar solvents dissolve nonpolar compounds best. Like dissolves like. Strongly polar compounds like sugar or ionic compounds like inorganic salts dissolve only in very polar solvents like water, while strongly nonpolar compounds like oils or waxes dissolve only in very nonpolar organic solvents like hexane. Similarly, water and hexane, or vinegar and vegetable oil, are not miscible with each other and will quickly separate into two layers even after being shaken well: polar protic and polar aprotic. Solvents with a relatively static permeability greater than 15 can be further divided into protic and aprotic. Protic solvents solvate anions, negatively charged solutes, strongly via hydrogen bonding. Water is a protic solvent, and we'll talk much more about that in chapter 16 and 19. Notice the polar protic solvents. Water is at the bottom of the list, and see how large the dielectric constant is. And the dipole is 1.85, which is fairly high. But the boiling points of the others that are high boiling points have very low dielectric. So here are some nonpolar solvents, and you can see the dielectric is very low, not too far from 1, very little dipole, if any. Diethyl ether has a little bit of 1 because of the oxygen between the two ethyls, or methyls in the case of dimethyl ether. And then here are some polar aprotic solvents, and fairly low. Now, acetone has a fairly high solubility for certain substances that you would think it wouldn't have. But acetone, as you well know, the ultimate fingernail polish remover. You can buy it in any store to remove fingernail polish and other things as well, glue and paint, etc. Aprotic solvents such as acetone and dichloromethane tend to have large dipole moments, separation of partial positive and partial negative charges within the same molecule, and solvate positively charged species via their negative dipole. This was taken from Wikipedia solvent, and you could read that for more information. When an ionic solid dissolves, the ions become solvated or surrounded by solvent molecules, and this is a figure that demonstrates that. Oil and water do not mix. Oil is less dense than water, so it floats on top. The colors result from the bending of light rays, refraction of light, by the thin film of oil. A solution conducts electricity if it contains ions. Here's A. Sodium chloride, a strong electrolyte, is nearly 100% dissociated into ions in water. Remember, water does not conduct electricity. This is B. Mercury 2 chloride, a weak electrolyte, is only partially dissociated in water. So the Mercury 2 chloride is a weak electrolyte. And then C, glucose, a non-electrolyte, does not dissociate in water. So it doesn't break down into ions. It just stays as an individual particle. Remember the glowing pickle that you read about in Connecting to Your World? The pickle contained an electrolyte. An electrolyte is a compound that conducts an electric current when it is in an aqueous solution or in the molten state. Conduction of electricity requires ions that are mobile and thus able to carry an electric current. All ionic compounds are electrolytes because they dissociate. The discussion of Gatorade was essentially about electrolytes. Let me read the last part of that slide again. It said, conduction of electricity requires ions that are mobile and thus able to carry an electrical current. All ionic compounds are electrolytes because they dissociate into ions. That's not altogether true because there are some ionic compounds that are not soluble in water. However, here are some nutrients: sodium, chloride, magnesium, potassium, and calcium. Here are some deficiency symptoms. The chloride, changes in pH, irregular heartbeat, for instance. Food sources: table salt, some fruits and vegetables, tomatoes, lettuce, olives, etc. You can read that: sodium, chloride, magnesium, potassium, calcium. So very important. You'll find a lot of that in Gatorade and things like that. Here is a galvanic cell. You see, we'll talk about oxidation and reduction a little bit later. Oxidation is the losing of electrons. Reduction is the gaining of electrons. You have cations, you have anions, you have a cathode, you have an anode. Here is copper and zinc. What's giving off electrons, what's gaining electrons, etc. What's the salt bridge for, etc. Sodium chloride, copper 2 sulfate, and sodium hydroxide are typical water-soluble electrolytes. Barium sulfate is an ionic compound that cannot conduct electricity in aqueous solution because it is insoluble, but it can conduct in the molten state. A compound that does not conduct an electric current in either aqueous solution or molten state is called a non-electrolyte. Many molecular compounds are non-electrolytes because they are not composed of ions. So you can have electrolytes that don't dissolve but are in the molten state. They will. Most compounds of carbon, such as table sugar, sucrose, and the alcohol in rubbing alcohol, 2-propanol, are non-electrolytes. Most compounds of carbon, such as table sugar, sucrose, and the alcohol in rubbing alcohol, 2-propanol, are non-electrolytes. Some polar molecular compounds are non-electrolytes in the pure state, but become electrolytes when they dissolve in water. This occurs because such compounds ionize in solution. For example, neither ammonia nor hydrogen chloride is an electrolyte in the pure state. Yet an aqueous solution of ammonia conducts electricity because ammonium ions, NH4+1, and hydroxide ions, -1, form when ammonia dissolves in water. And there's the equation, and there are the ions on the right side, and they will actually do the conduction of electricity. So they will become electrolytes when dissolved in water, and water will become an electrolytic solution when it has something dissolved in it. Similarly, in aqueous solution, hydrogen chloride produces hydronium ions and chloride ions. An aqueous solution of hydrogen chloride conducts electricity and is therefore an electrolyte. Not all electrolytes conduct an electric current to the same degree. In the simple conductivity test shown in Figure 9, a bulb glows brightly when electrodes attach to it and are immersed in a sodium chloride solution. The bright glow shows that sodium chloride is a strong electrolyte because nearly all of the dissolved sodium chloride exists as separate Na+1 and Cl-1 ions. When the hydrogen chloride is dissolved in water, it's actually called hydrochloric acid. Hydrochloric acid, even in the dilute state, is a strong electrolyte, and it creates a strong electrolytic solution. The ions move in solution and conduct an electric current. Most soluble salts, and inorganic bases are strong electrolytes. The bulb glows dimly when the electrodes are immersed in a mercury 2 chloride solution because mercury 2 chloride is a weak electrolyte. A weak electrolyte conducts electricity poorly because only a fraction of the solute in the solution exists as ions. Other weak electrolytes are ammonia and organic acids and bases. In a solution of glucose, the bulb does not glow. Glucose is let me change the timing. Glucose, C6H12O6, is a molecular compound. It does not form ions, so it is a non-electrolyte. Electrolytes are essential to all metabolic processes. Sodium and potassium ions control nerve impulse transmission and muscle contraction. If renal function is impaired or malabsorption from the gut disturbs optimum sodium and potassium levels, then serious nervous system problems arise. Loss of consciousness or difficulty in maintaining muscle coordination could result. Any condition that causes prolonged bouts of diarrhea can be life-threatening because of the dramatic loss of electrolytes. Electrolytes are excreted through the skin via sweat, and they must be replenished or cramps and heat stroke may occur. Sports drinks are a good source of electrolytes. They contain sodium, potassium, and calcium. Now, diarrhea, arsenic poisoning, and cholera cause terrible diarrhea, and you essentially die of dehydration or the loss of some of these important electrolytes. When an aqueous solution of copper 2 sulfate is allowed to evaporate, deep blue crystals of copper 2 sulfate pentahydrate are deposited. The chemical formula for this compound is CuSO4.5H2O. Water molecules are an integral part of the crystal structure of copper 2 sulfate pentahydrate and many other substances. The water contained in a crystal is called the water of hydration or water of crystallization. A compound that contains water of hydration is called a hydrate. In writing the compound of a hydrate, use a dot to connect the formula of the compound and the number of water molecules per formula unit. Formula unit is for ionic compounds. Crystals of copper 2 sulfate pentahydrate always contain 5 molecules of water for each copper and sulfate. Let me change the timing. Let me redo that sentence. In writing the formula of a hydrate, use a dot to connect the formula of the compound and the number of water molecules per formula unit. Crystals of copper 2 sulfate pentahydrate always contain 5 molecules of water for each copper and sulfate ion pair. The deep blue crystals are dry to the touch. They are unchanged in composition or appearance in normally moist air. A very interesting experiment you can do with copper 2 sulfate. Water can be driven from the hydrate by heating. Heating the sample of blue copper 2 pentahydrate begins. After a time, it turns white. And it turns white because the water is being driven from it. It's the water bound in the crystals that gives it its characteristic blue color. It gives it a blue color, and when you drive the water out of it, it turns white. But when heated above 100 degrees Celsius, the crystals lose their water of hydration. If anhydrous copper 2 sulfate is treated with water, the blue pentahydrate is regenerated. It's also very exothermic. Another compound that changes color in the presence of moisture is cobalt 2 chloride. A piece of filter paper that has been dipped in an aqueous solution of cobalt 2 chloride and then dried is blue in color, anhydrous copper 2 chloride. But As you can see in figure 11 on the next slide, when the paper is exposed to moisture, it turns pink because of the formation of the hydrate cobalt 2 chloride hexahydrate, the COCl2, and then the 6 water molecules bound into its crystalline structure. The blue paper could be used to test for the presence of water. Anywhere you could have any number of industrial or scientific applications. Here is paper treated with anhydrous cobalt 2 chloride is blue. In the presence of moisture, the paper turns pink. So it can be used both scientifically and industrially. The forces holding the water molecules in hydrates are not very strong, so the water is easily lost and regained. Because the water molecules are held by weak forces, hydrates often have an appreciable vapor pressure. If a hydrate has a vapor pressure higher than the pressure of water vapor in the air, the hydrate will lose its water of hydration or effloresce. For example, copper 2 sulfate pentahydrate has a vapor pressure of about 1 kPa at room temperature. The average pressure of water vapor at room temperature is about 1.3 kPa. Copper 2 sulfate pentahydrate is stable until the humidity increases. When the vapor pressure drops below 1 kPa, the hydrate effloresces. Washing soda or sodium carbonate decahydrate, there's the formula, is efflorescent. As the crystals lose water of hydration, they effloresce and become coated with a white powder of anhydrous sodium carbonate, that's Na2CO3. Hydrated salts that have a low vapor pressure remove water from moist air to form higher hydrates. These hydrates and other compounds that remove moisture from the air are called hygroscopic, like hygrophobia. For example, calcium chloride monohydrate spontaneously absorbs a second molecule of water when exposed to moist air. There's the equation. Calcium chloride is used as a desiccant in the laboratory. A desiccant is a substance used to absorb moisture from the air and create a dry atmosphere. For example, anhydrous calcium chloride can be placed in the bottom of a tightly sealed container called a desiccator. Substances that must be kept dry are stored inside, and it really works. A desiccator, it takes the moisture out of air. A solid desiccant such as calcium sulfate can also be added to a liquid solvent to keep it dry. A bottle labeled dry ethanol may have solid calcium sulfate at the bottom. The calcium sulfate does not dissolve appreciably in the solvent but absorbs water from the ethanol and keeps it dry. When a desiccant has absorbed all the water it can hold, the salt can be returned to its anhydrous state by heating. The reason you would put it in ethanol is because you can't separate water and ethanol completely. If you took a 50-50 mixture of ethanol and water and you distilled it, it would end up to be 80% ethanol and 20% water. If I distilled it again, it would be 87-13 ethanol. You would have to separate it, you would have to distill it maybe 4 or 5 times to get down to 95.4, 96% ethanol and 4% water. So there's no such thing as 100% ethanol, but what you can do is you can put things in the ethanol, such as calcium sulfate, in order to absorb that last bit of water. And that last bit of water that's absorbed makes the ethanol dry ethanol. Now, if you open that bottle or took out the calcium sulfate, it would spontaneously absorb atmospheric moisture. So the inability of alcohol, ethanol, and water to be separated is not unusual in nature. Matter of fact, they're called azeotropes. The inability of two substances to be uncombined it's an example of an azeotrope. Ethanol and water, you cannot distill them, you can't separate them completely, 100% completely. Deliquescent substances can remove water from the air. Sodium hydroxide pellets absorb moisture from the air. Eventually, a solution is formed. The word is deliquescent. Deliquescent substances can remove water from the air. Have you ever noticed the small packets of silica gel that are often packaged with electronic equipment and leather goods? Although the structure of the silica gel is not the same as a hydrated salt, it is hygroscopic substance used to absorb moisture from the air to prevent damage to sensitive equipment and materials. Some compounds are so hygroscopic that they become wet when exposed to normally moist air. These compounds are deliquescent, which means that they remove sufficient water from the air to dissolve completely and form solutions. Figure 13 shows that pellets of sodium hydroxide are deliquescent. That's the previous slide. For this reason, containers of sodium hydroxide and other chemicals should always be tightly stoppered, and the chemicals should never be touched by the fingers. Deliquescent, hygroscopic. The solution formed by a deliquescent substance has lower vapor pressure than that of the water in the air. Hygroscopic is the ability of a substance to attract and hold water molecules from the surrounding environments. This is achieved through either absorption or adsorption, with the absorbing or adsorbing material becoming physically changed somewhat by an increase in volume, stickiness, or other physical characteristics of the material as water molecules become suspended between the material's molecules in the process. Deliquescent, hygroscopic, adsorption, as opposed to absorption. Absorption, adsorption, or absorption. They're different words. Make sure you understand the difference between absorption and adsorption. Adsorption and absorption. I'm going to read, I have a computer here, and I'm going to read the first paragraph from Wikipedia on ab and adsorption. Adsorption, adsorption is the adhesion of atoms, ions, or molecules from a gas, liquid, or dissolved solid to a surface. This process creates a film of the adsorbate on the surface of the adsorbent. This process differs from absorption, in which a fluid permeates or is dissolved by a liquid or solid. Adsorption is a surface-based process, while absorption involves the whole volume of the material. So adsorption is the adhesion of atoms, ions, or molecules from a gas, liquid, or dissolved solid to the surface. Absorption, in which a fluid permeates or is dissolved by a liquid or a solid. Adsorption versus absorption. While some similar forces are at work here, it is different from capillary attraction, a process where glass or other solid substances attract water but are not changed in the process. For example, water molecules becoming suspended between the glass molecules. Hygroscopic substances include cellulose fibers such as cotton and paper, sugar, caramel, honey, glycerol, ethanol, methanol, diesel fuel, sulfuric acid, methamphetamine, many fertilizer chemicals, many salts including table salt, and a wide variety of other substances. Zinc chloride and calcium chloride, as well as potassium hydroxide and sodium hydroxide, and many different salts are so hygroscopic that they readily dissolve in water. They absorb, let me change the timing on that. Let me read that again. Zinc chloride and calcium chloride are hygroscopic, as well as potassium hydroxide and sodium hydroxide, and many different salts are so hygroscopic that they readily dissolve in the water they absorb. Are so hygroscopic that they readily dissolve in the water they absorb. This process is called deliquescence. So these chemicals will readily dissolve in the water that they absorb. They're hygroscopic, so they absorb water, and they're deliquescent because they dissolve in the water they absorb. Not only is sulfuric acid hygroscopic in concentrated form, but its solutions are hygroscopic down to concentrations of 10% or below. A hygroscopic material will tend to become damp and cake when exposed to moist air, such as the salt inside salt shakers during humid weather. Because of their affinity for atmospheric moisture, hygroscopic materials might require storage in sealed containers. When added to foods or other materials for the express purpose of maintaining moisture content, such substances are known as humectants. Materials and compounds exhibit different hygroscopic properties, and this difference can lead to detrimental effects such as stress concentration in composite materials. Differences in hydroscopy can be observed in plastic laminated paperback book covers. Often, in a sudden moist environment, the book cover will curl away from the rest of the book. The unlaminated side of the cover absorbs more moisture than the laminated side and increases in area, causing a stress that curls the cover towards the laminated side. This is similar to the function of a thermometer's bimetallic strip. Inexpensive dial-type hygrometers make use of this principle using a coiled strip. Hygrometers. The seeds of some grasses have hygroscopic extensions that bend with changes in humidity, enabling them to disperse over the ground. An example is needle and thread. Each seed has an awn that twists several turns when the seed is released. Increased moisture causes it to untwist, and upon drying, to twist again, thereby drilling the seed into the ground. Thorny devils collect moisture in the desert via nighttime condensation of dew that forms on their skin and is channeled to their mouths in hygroscopic grooves between the spines of their skin. Water also collects in these grooves when it rains. Capillary action allows the lizard to suck in water from all over its body. Deliquescent material are substances, mostly salts, that have a strong affinity for moisture and will absorb relatively large amounts of water from the atmosphere if exposed to it, forming a liquid solution. Deliquescent salts include calcium chloride, magnesium chloride, zinc chloride, potassium carbonate, potassium phosphate, carnolites, ferric ammonium citrate, potassium hydroxide, and sodium hydroxide. Owing to their very high affinity for water, these substances are often used as desiccants, which is also an application for concentrated sulfuric and phosphoric acids. These compounds are used in the chemical industry to remove the water produced by chemical reactions. Here's a problem which says, calculate the percent by mass of water in washing soda, sodium carbonate decahydrate. There's the formula, N2CO3 and 10 H2Os. So it's the total mass of the water divided by the total mass of the compound. Total mass of water divided by total mass of the compound, 180 divided by 286 times 100 is 63%. 63% water, that's very high. Here is a table with many hydrates that are used in the chemical industry and in the laboratory. Epsom salts, which athletes use, they soak in Epsom salts in the bath and they relieves muscle tension and strain and aches and such. That's magnesium sulfate heptahydrate. Suspension. Now we're going to look at suspensions and colloids and how they differ from solutions. We're going to look at suspension. So far in this chapter, you have learned about homogeneous mixtures that are formed when compounds such as inorganic acids, bases, and ionic salts mix with water. These mixtures are classified as solutions. In contrast, heterogeneous mixtures are not solutions. If you shake a piece of clay with water, the clay breaks into fine particles. The water becomes cloudy because the clay particles are suspended in the water. But if you stop shaking, the particles begin to settle out. The particles in a typical suspension have an average diameter greater than 1,000 nanometers, which is 1 micrometer. By contrast, the particle size in a solution is usually about 1 nanometer or less. The larger size of suspended particles means that gravity plays a larger role in causing them to settle out of the mixture. Cooks use suspensions of flour or cornstarch in water to thicken sauces and gravies. These mixtures must be shaken or stirred immediately before use because the suspended particles settle out. They quickly settle out. Suspensions, gravies, etc. Suspensions are heterogeneous because at least two substances can clearly be identified. In the example of clay particles mixed with water, you can clearly see the dispersed phase, clay, in the dispersion medium, water. Figure 14 shows that if muddy water is filtered, the filter traps the suspended clay particles and clear water passes through. That's a very important distinction. Suspensions can be filtered. Here's an example of a suspension of muddy water. You shake it up and it looks like it's not going to settle and it looks like it's a constituted solution, and then all of a sudden you'll start to see things settle, and eventually the water will be clear, and then at the bottom is the mud. This could be filtered. If you were very specific, you could filter it, and that's a distinction between suspension and what we'll talk about next. Colloids can't be filtered. The material that's in the water can't be trapped. So a colloid is kind of an intermediate mixture between a suspension and a solution. Now we're going to start colloids. There is more in the next few slides than on any concept in the entire video. Colloids is a very important concept in chemistry. It's very misunderstood. It's not studied very much, but it is indeed one of the most important aspects in all of chemistry. Remember, how the molecules are arranged when they react is critical in terms of chemical reactions. Gelatin is a type of mixture called a colloid. A colloid is a heterogeneous mixture containing particles that range in size from 1 nanometer to 1,000 nanometers, or 1 nanometer to 1 micrometer. The particles are spread throughout the dispersion medium, that's the solvent in quotes, which can be a solid, liquid, or gas. The first substance to be identified as colloids were glues. Other colloids include such mixtures as, let me change the timing. The first substances to be identified as colloids were glues. Other colloids include such mixtures as gelatin, paint, aerosol sprays, and smoke. Now on the bottom you'll see a conversion, unit label conversion, which shows you really the size of nanometers. There's 1 billion nanometers in 1 meter and 1 million micrometers in 1 meter. That's just to give you a little perspective. Remember, a solution is nanometer size, a colloid is between a nanometer and a micrometer, and a suspension is greater than a micrometer. Here is a table of colloids. Now, you see you have 2 columns on the left. The dispersed phase, which would be the solute, quote-unquote solute, and then the dispersion medium, which would be the solvent. A solute and a solvent are terms used in solutions. This is not a solution. However, dispersed phase is analogous to the solute, and the dispersed medium is analogous to the solvent. So, if you put a gas into a liquid, you get foam. That's an example would be whipped cream. So you have the dispersed phase, you have the dispersion medium, like the solvent, and then you have the type of colloid it is, and then you have an example. So you have many examples there, and you could certainly add to them. And so that's colloids, table 3, dispersed phase, and dispersed medium. Table 3 lists some common colloidal systems and gives examples of familiar colloids. How do the properties of colloids differ from those of suspensions and solutions? Like suspensions, many colloids are cloudy or milky in appearance when they are concentrated. Like solutions, colloids may look clear or almost clear when they are dilute. The important difference between colloids and solutions and suspensions is the size of the particle. The colloid is between 1 micrometer and 1 nanometer. Colloids have particles smaller than those in suspensions and larger than those in solutions. These intermediate-sized particles cannot be retained by filter paper, as are the larger particles of a suspension, and they do not settle out with time. Colloids can be distinguished by the Tyndall effect and by the observation of Brownian motion. They are also subject to coagulation or clumping together, and they can be emulsified or made stable. Here are some examples of colloids: foam, a sol, which is like a paint, emulsion, aerosol, gel, there's another aerosol, a solid sol, such as pumice or marshmallows, some gems such as pearls, some precious stones are also colloidal in nature. I have a link for additional examples of colloids to give credit to the author there. Here is a example of the 3 different types: the solution, the colloid, and the suspension, as you go from left to right, and the light is shining through the 3 glass jars that are stoppered. You see no light scattered in the first one, that's going to be a solution. Then you see light scattered in the second one, that's a colloid, and then you actually see the particles in the suspension. So fog or mist is a colloid and thus exhibits the Tyndall effect. Particles in colloids and suspensions reflect or scatter light in all directions. Solutions do not scatter light. So there's the light source, there's A and B For instance, the little fog in the forest is really what they're talking about. The Tyndall effect, ordinarily you can't see a beam of sunlight unless the light passes through particles of water, mist, or dust in the air. These particles scatter the sunlight. Similarly, a beam of light is visible as it passes through a colloid. The scattering of visible light by colloidal particles is called the Tyndall effect. Tyndall effect. Suspensions also exhibit the Tyndall effect, but solutions do not. The particles in solutions are too small to scatter light. Figure 15 shows how the Tyndall effect can differentiate solutions from colloids and suspensions. Remember, solutions have particles less than 1 nanometer. Here again is figure 15, and you can see that the difference in the scattering of light is significant, going from solutions to colloids and suspensions. Suspensions are very easy in some ways to identify because if you wait a little bit, the particles will settle. So if they don't settle, then the next test would be the Tyndall effect to determine what it is. Brownian motion, flashes of light or scintillations are seen when colloids are studied under a microscope. Colloids scintillate because the particles reflecting and scattering light move erratically. The chaotic movement of colloidal particles, which was first observed by the Scottish botanist Robert Brown, 1773 to 1885, is called Brownian motion. Brownian motion is caused by collisions of the molecules of the dispersion medium with the small dispersed colloidal particles. These collisions help prevent the colloidal particles from settling. A very easy experiment to show in class. Coagulation colloidal particles also tend to stay suspended because they become charged by absorbing ions from the dispersion medium onto their surfaces. Some colloidal particles become positively charged by absorbing positively charged ions. Other colloidal particles become negatively charged by absorbing negatively charged ions. All colloidal particles, in particularly colloidal systems, will have the same charge, although the colloidal system is neutral. The repulsion between the like-charged particles prevents the particles from forming heavier aggregates that would have a greater tendency to settle out. Thus, a colloidal system can be destroyed or coagulated by the addition of ions having a charge opposite to that of the colloidal particles. The added ions neutralize the charged colloidal particles. The particles can clump together to form heavier aggregates and precipitate from the dispersion. An emulsion is a colloidal dispersion of a liquid in a liquid. An emulsifying agent is essential for the formation of an emulsion and for maintaining the emulsion stability. For example, oils and greases are not soluble in water. However, they readily form a colloidal dispersion if soap or detergent is added to the water. Soap and detergents are emulsifying agents. You can clearly see how one side is going to be organic on the left and the other side is going to be ionic on the right. The ionic attaches to the water, and the organic side, I think you should start calling things organic if they are organic, will stick to the organic material such as oil or grease or something of that nature. Soap, a cheap surfactant. The discovery of soap predates recorded history, going back perhaps as far as 6,000 years. Excavation of ancient Babylon uncovers cylinders with inscriptions for making soap around 2800 BCE. Later records from ancient Egypt, 1500 BCE, describe how animal and vegetable oils were combined with alkaline salts to make soaps. A very inexpensive soap. Just you combine fat with some alkali material and you heat it and you get soap. According to Roman legend, soap got its name from Mount Sapo, where animals were sacrificed. Rain would wash the fat from the sacrificed animals, along with alkali wooden ashes from the sacrificial fires, into the Tiber River, where people found the mixture helped clean clothes. This recipe for making soap was relatively unchanged for centuries, with American colonists collecting and cooking down animal tallow, which is rendered fat, and then mixing it with an alkali potash solution obtained from the accumulated hardwood ashes of their winter fires. Similarly, Europeans made something known as castile soap using olive oil. Only since the mid 19th century has the process become commercialized and soap become widely available at the local market. The basic structure of all soaps is essentially the same, consisting of long, hydrophobic, water-fearing hydrocarbon tail and a hydrophilic, water-loving anionic head, such as illustrated here. The only difference is that each one of these carbon-carbon bonds is at an angle to each other, as shown in a prior slide. But you have the negative anion because one of the hydrogens from the base is taken off, the OH, and that creates a negative ion known as an anion. The length of the hydrocarbon chain, N meaning the number of carbons that are in the chain, varies with the type of fat or oil, but is usually quite long. What I showed you on the former slide is a very short example. The anionic charge on the carboxylate head is usually balanced by either a positively charged potassium, K+, or sodium, Na+, cation. In making soap, triglycerides in fat or oils are heated in the presence of a strong alkali base such as sodium hydroxide, producing 3 molecules of soap for every molecule of glycerol. And if you want to read more, there's the link. This was taken from Chemistry Explained. Here is an example of what the soap does. The soap mixes with the oil and forms a micelle. It acts as a surfactant, and micelle is M-I-C-E-L-L-E. And it forms the micelle, and you can see the tacks represent the soap, and the head of the tack is ionic and is attracted to the water molecules, and things are swept away. Like synthetic detergents, soaps are surface active substances called surfactants, and as such make water better at cleaning surfaces. Water, although a good general solvent, is unfortunately also a substance with very high surface tension. Because of this, water molecules generally prefer to stay together rather than to wet other surfaces. Surfactants work by reducing the surface tension of water, allowing the water molecules to better wet the surface and thus increase water's ability to dissolve dirty oil and stains. So you need that surfactant to reduce the hydrogen bonding, thereby reducing the surface tension. Here's a better illustration of the molecule I have shown you, and the oxygen is blue, the carbon is red, the hydrogen is yellow, and the only difference between this and something else would be, or something in real life, would be that the carbon chain is very, very long, and each carbon-carbon bond is at an angle to one another, approximately 105 degrees. And let's start calling, like I said before, the CH end of the molecule on the left, where you have all the hydrogens and carbons. Let's start calling that the hydrocarbon end, or better, the organic end. This organic end will dissolve like substances, other organic, very general terms, other organic substances. Now, that's called the hydrophobic end. That's called the hydrophobic end. So the other end, the anion, or negatively charged N, -1 charge, results from a alkali substance, such as, and we'll learn that better when we're in 19, what an alkali substance is. So you take an alkali substance and that removes the H from the OH, and as a result you form an anion, negatively charged, and that anion is highly attracted to the polar water. That's called the hydrophilic, inorganic end of the molecule that bonds with water. And so the left side of the molecule will dissolve the oil, and the right side of the molecule will be attracted to the water, and things will, as I said before, wash away. Here's a perfect example of how an emulsifier works. A, going from top down, A is two immiscible, not miscible, not combined, you can't combine them, are not yet emulsified. B, an emulsion of phase 2 dispersed in phase 1. The unstable emulsion progressively separates. The surfactant outline of the particles, it kind of coats the particles, positions itself on the interfaces between phase 2 and phase 1, stabilizing the emulsion. So you have one phase is going to be the dispersion medium, and the other phase is going to be the dispersed medium. Here's a better example of a micelle. Now, these are blow-ups of what really exists, but in, for instance, milk, which is approximately 4% fat, if it wasn't for some kind of ability to form an emulsion, you would be able to see the fat floating on the surface of the water part of the milk. So these are called micelles. What is an emulsifier? An emulsifier can make an emulsion more stable by making the oil droplets stay in the water for a longer time. Examples of food emulsifiers are mustard, egg yolk, the yellow bit in the middle. Mayonnaise is an emulsion of oil and water using egg yolk as an emulsifier. The mayonnaise also contains lemon juice and vinegar. How does an emulsifier work? An emulsifier molecule works by having two parts. One part of the molecule has an electric charge, like an ion, and will dissolve in water but not oil. This part of the molecule, known as the head, is called hydrophilic, which means water-loving. The other part, called the tail, is a long hydrocarbon, organic, which will dissolve in oil but not water. This part of the molecule is called hydrophobic, which means water-fearing. The picture below shows the hydrophilic head and the hydrophobic tail of an emulsifier molecule. Emulsifier showing hydrophobic head and hydrophilic tail. The head is pink or magenta, and the tail, the hydrophobic bit, that's going to be cyan or blue in this particular example. The emulsifier molecule dissolves with its head in the water and its tail in the oil droplet. A large number of emulsifier molecules are needed to keep the oil droplet dispersed in the water for a long time. The picture above shows how the emulsifier molecules position themselves to make an oil droplet more stable. And you can see how the pink portion is going to be the hydrophilic, and that'll be attached to the water. And this oil droplet is actually very, very small. And the emulsifier, which is kind of into the oil droplet, is actually a mechanical device to keep it suspended in the water. And it will stay so indefinitely. And that's one of the differences between a colloid and a suspension. Here's another example of a good emulsion. You have various things like coalescence, creaming, flocculation, breaking, but a good emulsion keeps everything well distributed and the droplets of the oil base or organic based material very small, so that it can be supported by the water and remain in quote-unquote solution. I use that in quotes. It's not really a solution, of course. Here are some things that are colloids, or they're trying to be colloids, and you have the coagulation of the material, and that will soon settle out. So it's not a perfect emulsion. One end of a large soap or detergent molecule is polar and is attracted to the water molecules. The other end of the soap or detergent molecule is nonpolar and is soluble in oil and grease. Soaps and other emulsifying agents thus allow the formation of colloidal dispersions between liquids that do not ordinarily mix. Figure 16 below shows a familiar example of an emulsion, mayonnaise. Mayonnaise is a heterogeneous mixture of oil and vinegar, and it is in actuality the egg yolk which acts as the emulsifying agent that keeps everything well mixed. And it obviously, you can keep mayonnaise around for quite a while and it stays locked in one obvious phase. So it is indeed not a suspension. It is certainly not a solution, but it is a colloid. Such a mixture would quickly separate without the presence of egg yolk, which is the emulsifying agent. Other foods such as milk, margarine, and butter are also emulsions. Cosmetics, shampoos, and lotions are formulated with emulsifiers to maintain consistent quality. Table 4 on the next slide summarizes the properties of solutions, colloids, and suspensions. The addition of egg yolk to a mixture of oil and vinegar produces mayonnaise, a stable emulsion. Now, the next few slides are going to summarize much of what we've been talking about, from solutions that are a 0.1 nanometer to 1 nanometer, to the size of a colloid, 1 to 1,000 nanometers or 1 micrometer, and then 1 micrometer or larger. Those are suspensions. Now, you're going to have scattering, no scattering, Tyndall effect, effect of gravity, filtration, uniformity, particle size. It would be a very good idea to commit to memory as much of this table as you can. It summarizes so much of the work that we've been doing in chapter 15. Now let's review specifically colloids for a while. When dispersion medium is a solid, this is case 1, dispersion medium is solid. In other words, the solvent, quote unquote, solvent is a solid solvent. So in other words, salt in water. Salt is the dispersed phase. The salt is the dispersed phase, and the liquid is the dispersed medium. So in this particular case 1, the water that's solvent is going to actually be a solid. So a solid solid or solid sol would be gemstones or pearls. A liquid in a solid would be cheese, butter, jellies. Those are called gels. A gas in a solid would be called a solid sol, such as pumice or foam rubber. So I'm going to have 3 cases. The first case is dispersed medium is a solid, and then we'll change the dispersed medium from a solid to a liquid and then to a gas. Followed by examples of each preceding slide. The examples that are given are going to follow the slide. So here we have cheese, which is gel. We have solid sols. There's another shot of gels, solid sol, and finally another solid sol, and that is going to be pearls and some types of precious stones. Now, case 2, when dispersion medium is a liquid, the dispersed phase can be solid, liquid, or gas. Based on the state of dispersed phase, colloids are called sols, emulsions, or foam. Different types of colloids and examples of each type are given below and on the next slide. So a solid into a liquid are called sols. Those are paints, muddy water. Liquid or emulsion, that's very familiar to you by now. Milk, hair, cream. A gas in a liquid would be soap lather or whipped cream. Let me just say something about muddy water. Muddy water could be a suspension, or it could be a colloid, depending upon the size of the material that's making the muddy water. For instance, some muddy water simply doesn't settle, it stays muddy, because the particles are light enough to maintain the integrity of the colloid. We have paint, which is a sol. We have froth, whipped cream, milk, again muddy water, and soap lather. These are case 2, solid into a liquid, liquid into a liquid, and gas into a liquid. Now this is case 3. Dispersion medium is a gas. When dispersion medium is gas, the dispersed phase can be solid, liquid, but not gas. It is important to note that colloid is a heterogeneous mixture. When gas is mixed with another gas, it forms a completely miscible, homogeneous mixture and not a colloidal solution. Though 3 states, solid, liquid, and gas, each for dispersed medium and dispersed phase can form 9 different combinations, we only have 8 colloidal states. Colloids of gas with dispersed phase of solids and liquids are called aerosols. Big in the news, aerosols. Different types of colloids and examples of each type are given below on the next, it's actually on the next slide is going to be the chart. There it is. And then on the next slide are going to be the examples. All the types here are aerosol, solid in a gas, dust, or smoke. Now remember, the particle has to be small enough to maintain the colloid. It has to stay in the air. And liquid in gas would be an insecticide spray, fog, or clouds, where, again, the size of the particle has to be between 1 nanometer and 1 micrometer. Here are some examples of clouds, dust, and fog. And again, be careful that the size of the particle, you can have clouds or aerosols, and the dispersed medium is large, so things settle, and that's a suspension. So this can be a solution, this can be a colloid or a suspension specifically. So again, remember of the type of particle that's being put into the dispersion medium. Now we're going to compare solutions, colloids, and suspensions in a table together, and we can see one relative to the next. Now the first table looks at solutions. We have gas, which is air, liquid gas, solid gas, we have none here. We have gas and liquid, oxygen in the air, oxygen and water. We have a liquid, alcoholic beverages, solid liquid, sugar and water, a gas solid, hydrogen in metals, a liquid in a solid would be an amalgam, mercury, which is a liquid at room temperature, of course, in gold, And then a solid would be alloys, plasticizers in plastics. In other words, alloys would be brass, bronze, those would be alloys, or a homogeneous combination of two or more substances resulting in one phase, copper and nickel, etc. Here are colloids, and we have the various types. We have gas, gas, none, liquid gas, we are aerosol, solid and gas or solid aerosol, gas, liquid, foam, liquid emulsion such as mayonnaise. Solid and liquid would be pigmented ink or blood. A gas in a solid would be solid foam. Liquid in a solid would be a gel, and a solid in a solid would be a solid salt. Notice I have at the top of the column solute and solvent. I meant to put quotes around them, but it was easier to fit the third column in. So those really are not, those are fictitious definitions, solute and solvent. And here is a suspension. Again, solute and solvent is fictitious. We have a liquid and a gas. We have all of these others. I won't go through it. And these are suspensions where you have this coarse dispersion, heterogeneous mixture. Dispersed phase is greater than 1 micrometer. So those are the comparisons of the three combinations we're looking at. The solution, which is a homogeneous combination resulting in one phase with particles less than 1 nanometer. We have colloids, same thing, homogeneously combined, but it's not defined as homogeneous. It's defined as heterogeneously combined, and it has particles between 1 nanometer and 1 micrometer. A cement is a binder, a substance that sets and hardens as the cement dries and also reacts with carbon dioxide in the air dependently and can bind other materials together. The word cement traces to the Romans, who used the term opus cementitium to describe masonry resembling modern concrete that was made from crushed rocks with burnt lime as binder. The volcanic ash and pulverized brick additives that were added to the burnt lime to obtain a hydraulic binder were later referred to as cementum, various ways, or cement. Cements used in the construction can be, let me change the timing. Cements used in construction can be characterized as being either hydraulic or non-hydraulic. See also hydraulic and non-hydraulic lime plaster. This is taken from Wikipedia, and you can read about this further. Additional information, notes on it will be given extra credit. Hydraulic cement is made by replacing some of the cement in a concrete mix with activated aluminum silicates or pozzolanas, such as fly ash, to activate cement setting in wet conditions or underwater, and further protects hardened concrete from chemical attack. Example, Portland cement, hardening because of hydration. The chemical process for hydraulic cement found by ancient Romans used volcanic ash, which is activated aluminum silicates, to activate cement hardening between the anhydrous cement powder and the water or plaster, and water instead of relying on water drying out and simultaneously, let me change the timing, let me reread that sentence. The chemical process for hydraulic cement found by ancient Romans used volcanic ash, activated aluminum silicates, to activate cement hardening between the anhydrous cement powder and water or plaster and water instead of relying on water drying out and simultaneously reacting with airborne carbon dioxide. The Romans built some beautiful monuments, and they couldn't have done that without the cement. Thus, cement can harden underwater or when constantly exposed to wet weather. The chemical reaction results in hydrates that are not very water soluble and so are quite durable in water and from chemical attack. Non-hydraulic cements and plasters do not harden in wet conditions. The most important uses of cement are as an ingredient in the production of mortar in masonry and of concrete, a combination of cement and an aggregate to form a strong building material. Presently, cheaper, pollution-free fly ash from power stations or other waste or by products are used as pozzolanas with plain cement to produce hydraulic cement. Pozzolanas can replace up to 40% of Portland cement. Non-hydraulic cement such as slaked limes, calcium hydroxide mixed with water, harden due to the reaction of carbonation in presence of carbon dioxide, naturally present in the air. Calcium oxide is produced by lime calcination at temperatures above 825 degrees Celsius for about, let me change the timing, that's for about 10 hours at atmospheric pressure, and its calcium carbonate yields calcium oxide plus carbon dioxide. That's balanced as it is written. The calcium oxide is then spent mixing it to water to make slaked lime. Very complicated but very simple chemical reactions occur in the cement. Once the water in excess from the slaked lime is completely evaporated, this process is technically called setting. The carbonation starts. There's the carbonation reaction. This reaction takes a significant amount of time because the partial pressure of carbon dioxide in the air is small. The reaction of carbonation requires the air to be in contact with the dry cement. Hence, for this reason, the slaked lime is a non-hydraulic cement and cannot be used under water. Conversely, the chemistry ruling the action of hydraulic cement is the hydration. Hydraulic cements, such as Portland cement, are made of a mixture of silicates and oxides, the four main components being belite, which is 2 calcium oxide, silicon oxide, and then alite, cellite, and brown millerite. Very complicated looking formulas. Then the reactions during the setting of the cement are all of those as follows, and you can see how they're all hydrating the hydrate. The anhydrous form is being hydrated in each one of those reactions. And during the hardening, the chemistry of the reaction of hydration is still not completely clear. So you can say that it is water that holds cement together. When the water leaves, then you get complete mess. You get a powder. The silicates are responsible of the mechanical properties of cement. The cellite and the brown millerite are essential to allow the formation of the liquid phase during the cooking. The chemistry of the above listed reaction is not completely clear and is still the object of research. An early version of cement made with lime, sand, and gravel was used in Mesopotamia in the 3rd millennium BC and later in Egypt. It is uncertain where it was first discovered that a combination of hydrated non-hydraulic lime and a pozzolan produces a hydraulic mixture. See also pozzolanic reaction. But concrete made from such mixtures was first used by the ancient Macedonians, and 3 centuries later on a larger scale by Roman engineers. They used both natural pozzolans, trass or pumice, and artificial pozzolans, ground brick or pottery, in these concretes. Many excellent examples of structures made from these concretes are still standing, notably the huge dome of the Pantheon in Rome and the massive baths of Caracalla. The vast system of Roman aqueducts also made extensive use of hydraulic cements. Although any preservation of this knowledge in literary sources from the Middle Ages is unknown, medieval masons and some military engineers maintained an active tradition of using hydraulic cement in structures such as canals, fortresses, harbors, and shipbuilding facilities. The technical knowledge of making hydraulic cement was later formalized by French and British engineers in the 18th century. Modern hydraulic cements began to be developed from the start of the Industrial Revolution around 1800, driven by three main needs: hydraulic cement, render, stucco for finishing brick buildings in wet climates; hydraulic mortars for masonry construction of harbor works, etc., in contact with seawater; development of strong concretes. In Britain particularly, good quality building stone became ever more expensive during the period of rapid growth, and it became a common practice to construct prestige buildings from the new industrial bricks and to finish them with stucco to imitate stone. Hydraulic limes were favored for this, but the need for a vast set time encouraged the development of new cements. Most famous was Parker's Roman cement. This was developed by James Parker in the 1780s and finally patented in 1796. It was in fact nothing like material used by Romans, but was a natural cement made by burning septaria, nodules that are found in certain clay deposits and that contain both clay minerals and calcium carbonate. The burnt nodules were ground to a fine powder. This product made into a mortar with sand set 5 to 15 minutes. The success of Roman cement led other manufacturers to develop rival products by burning artificial mixtures of clay and chalk. That concludes the lecture. There are other sites on cements, and remember, I will give you extra credit for accessing them and taking notes and maybe even giving a presentation in class. Good luck on your test this week, and make sure you do as many of the homework problems as you can. Extra credit will be given for extras done.